We from the family of Step Up Bengal welcome all the CSIR NET, Math or SET exam aspirants to our next video lecture on classical mechanics. We have already discussed degree of freedom and generalized coordinate, which ultimately laid the foundation of Lagrangian mechanics. So, especially if we go through lecture 6, that is our previous video lecture, there you can see what is the basis of Lagrangian mechanics. But to derive all the expressions in Lagrangian mechanics, we need various important terms. One of those terms will be kinetic energy. What is it? If we ask anyone about it, the answer comes as it is half into m into velocity square, or in famous term half mv square. It is true that in Newtonian mechanics this is the expression for kinetic energy, where m is mass and v is velocity obviously, but it is rather the expression, not the definition of kinetic energy. To realize that at a glance, we must go through Newtonian mechanics and especially Newton's second law of motion, which tells us P equal to mf. P is force, m is mass, f is acceleration. Now take a look at the fact that whenever a particle starting at O wants to go in this way, and there is a strong opposite force in this particular direction, that is P, then if it starts from O with velocity v, and due to this strong force ultimately the velocity will diminish, and say after some time t it becomes 0. Now what will happen to this equation in that case? If we analyze this, just we would write the expression for f as v dv dx. Clear? Now one important thing is to realize in Lagrangian mechanics is work done. We should briefly revise it from our previous classes of say UG level, where work done was defined whenever a point moves from O to A, that is from a particular position to another, with the help of some force, then work done is defined as W equal to that force P dot X, and if this work done is a small amount of work done, then P dot dx. This expression is extremely important. That means P, that is a force, that is vector, and another dx, that is displacement, that is also a vector. So whenever we have some displacement, there must be some work done due to that force. Now if P is this one, then since the particle is starting with velocity v and after some time its velocity becomes 0, so we have some work done by that opposite force, that is the force against which it is diminishing its velocities. That is work done W, that is equal to, say in this period velocity becomes v to 0, so due to negative force we take negative sign, so what will be the result? V to 0 and then P dot dx. What was P? This integration is reversed 0 to V and negative sign eliminates. So P, what was P? P was here m into V into dv dx into dx. So ultimately this becomes m into V square by 2 from 0 to V, and that is ultimately becomes mv square with half outside. So half mv square is the expression for kinetic energy. This kinetic energy ultimately some kind of work done. Since its discovery, still now there is no particular expression for energy. Energy is something which will always be calculated by the help of work done. Now, if this is kinetic energy, then it is defined as the total amount of work done due to an opposite force or against force. Someone says it as against force. That means the force which is acting against the direction of motion. So the total amount of work done due to an against force or opposite force for which velocity of a particle comes from V to 0 will ultimately give us the expression for kinetic energy as half mv square. So from now on we will use this result for kinetic energy. What is it? Ultimately some kind of work done. That is very important concept which is often asked in the higher level interviews. So be careful about that. Half mv square is the expression for kinetic energy but not the definition, because kinetic energy is some type of work done which happens due to an opposite force. Clear? And from that and during that period velocity becomes v to 0. So ultimately the particle stops. So Lagrange ultimately comes out of Newtonian mechanics by using this energy system. Lagrangian mechanics is totally dependent upon energy system, and as we all know that energy is of two types. One we have already seen, kinetic energy. In short, this is Ke, and in Lagrangian system this is denoted as capital T by English letter capital T. So from now on, by kinetic energy we will just see capital T, or rather T will represent kinetic energy. We will in fact now have a gap here. We will come to it, fill this gap later in our lecture series. First of all, we should have all the expressions for kinetic energies in different coordinates. Say Cartesian. First of all, say Cartesian coordinates, two-dimensional. So what will be that? Half into m into v square. Now in two-dimensional motion, take a look at the fact that whenever a particle moves from P to Q, it has velocity in this particular direction, that is in x direction as x dot, and in y direction as y dot. So what will be its ultimate velocity? That will be the resultant, say, acting in this direction. What will be that resultant direction? That will be root over x dot square plus y dot square. So in Cartesian system 2D, expression for kinetic energy will be half m x dot square plus y dot square, that is T. In Cartesian system 3D, this t will become half into m into x dot square plus y dot square plus z dot square. Clear? So the expression for t in Cartesian system 2D and 3D are given here. These two expressions will be extremely important for tackling the problems in CSIR NET or any set exam of the states. Clear? Next comes polar coordinate system. Polar coordinate system. What was polar coordinate system? In Cartesian system, we see two mutually perpendicular axes, x-axis as well as y-axis. But in polar coordinate system, we have only one axis, that is OX. And a particle, say, moving in this curve is here at P. We denote its position by r and theta. This is r distance from a particular fixed point. This O is fixed, called pole. From its name comes polar. From pole its distance is r, and as it moves from, say, here A to P upward, so it is describing a particular angle that is denoted as theta. So this theta is an angle and this is a distance. And whenever a particle moves in polar coordinate system two-dimensional, then it has two velocities. One along polar axis, that means this axis. Polar axis is this one. This one is called polar axis. This one r is called radius vector. And the direction of r, this is important, just make a note of it carefully. Direction of r equal to radial direction. This is important. Whenever a particle is moving in polar coordinate system, we have just two important components. One is radial direction, that means along radius vector, it may be away from pole, that means in this direction, or towards pole, but the direction will always be along radius vector, so it is called radial. And the other one, which is perpendicular to this radius vector, this is called cross radial direction. So what is the relationship between radial and cross radial direction? Radial direction is always along, as I have already said, radius vector, and a direction which is perpendicular to the radius vector will always be called cross radial direction, or someone calls it as transverse. This is important. All these terms will be important to tackle the simple points in question paper in those exams, as I have already mentioned. Transverse direction, transverse or cross radial. So we have two particular direction. As in Cartesian system, all of you can see, as in Cartesian system we have two directions. আমাদের যেমন দুটো direction থাকে, x dot আর x axis এর আর y axis এর. So in polar coordinate system we have also two directions. These two directions will be important, not this one. This is the beauty and this is the comparative discussion between Cartesian treatment and polar coordinate system. In polar coordinate system, we give prime importance to the directions along radius vector and the direction along a line which is always perpendicular to the radius vector, that is cross radial direction. As in Cartesian system, the velocity along x-axis is x dot. So very similar treatment has been done on radial direction, and velocity in that direction is denoted by dr by dt. Someone calls it as r dot. And in cross radial, this r dot uh, uh, from diagrammic point of view, this r dot is very similar to x dot. X dot is along x-axis, this is along radius or radial axis. So the configuration here and here will be different. Just in physics we have so many configurations. In fact, one of the most important is polar coordinate system. So dr by dr dt, we mention it is a particular velocity, that velocity along radial direction, and it is denoted as vr also. But this expression is important for exam point of view. We should realize and use r dot. R dot means radial velocity, so we can call it as radial velocity. And the another direction is the direction along cross radial line. So along cross radial line, the velocity will be very similar to y dot. This treatment will be similar, and this becomes r theta dot. That means r into d theta by dt. This is denoted as v theta. But from exam point of view, this notation r d theta dt or r theta dot, this is important. So we have two important direction in polar coordinate system, and along those two directions we have already the expressions for velocity. We should write down here radial expression for radial velocity, that will be r dot. Expression for cross radial velocity will be r theta dot. Now, as in this particular case, the resultant of x dot and y dot was taken to be the ultimate velocity. Here also the resultant, say, will be in this direction. What will be that? Resultant velocity Vr, that will be root over r dot square plus r theta dot whole square. Very similar to this one, x dot square plus y dot square, same treatment. So it becomes ultimately root over r dot square plus r square theta dot square. Now using this velocity, we can easily derive kinetic energy T in this coordinate system, that means in polar 2D, as half m r dot square plus r square theta dot square. Now we should make a particular note of the point for exam perspective. This is important, very important point to note, that say this r equal to constant. Where does it happen? Say the particle is moving in a circle of radius a. Say this is of radius a. So r equal to a, that means r is constant. So in that case, what will be the final expression for kinetic energy? If r is constant, say a, then r dot will be 0. It is clear that the derivative of something which is constant will always be 0. So the kinetic energy T will become in that case half m r dot, but it is 0, plus here we should take r as a, so a square theta dot square. So ultimately this becomes half m into a square theta dot square. Now in this video we stop here with this important expression. Whenever r is constant, then this expression becomes this, the expression given below. But if we have the idea of this one, then we can easily derive this one. So no need to just panic about that we should just memorize this result. If you can easily realize what is given in this expression, then you can derive this result yourself in the exam hall or etc. But this is important conclusion, that we may have to use this concept. We will see later that in the questions of CSIR this concept is given. So in this video we stop here. with the expressions of kinetic energies. In the next lecture, we will discuss how kinetic energy capital T have its expressions in two more important coordinate systems. One is spherical polar coordinate system, and the last but not the least, that is cylindrical system. As Cartesian system is a particular system, cylindrical system or spherical polar coordinate systems are also very important configuration to describe the position of particles in physics especially. We will give special importance to these two coordinate systems because this will be extremely important from for exam perspective. So if you feel that you are getting some kind of help from our team, please like and comment. If you have any difficulty to realize what we have done. So until then, goodbye.